Okay, so for today, we are going to be going over a review of some of the equations that you guys have been learning in class recently and in past chapters, just to kind of refresh your mind on how to use these equations. We will also be doing a few different examples, one on rotational and translational kinetic energy, one on physical pendulum, one about momentum with a bullet and an object, and then one static equilibrium problem. And then if we have any extra time at the end, we'll be doing some closing questions from you guys. Okay, anything to add to that, Josh?
Nope, I think we're ready to go.
Okay. So for the first example, we have rotational and translational energy. There is a pulley with a radius r and a moment of inertia I, which are given, and it rotates without slipping. Two of the blocks are attached to the pulley, and we want to calculate the speed of the 4 kilogram block just before it hits the ground. So this is a setup for the problem. I will move it over to the whiteboard so that we can do some work. Okay. Okay. So we have the pulley with 2 boxes attached to it. One is 2 kilograms, and the other is 4. There is 5 meters between the 4 kilogram box and the ground. The 2 kilogram box is already on the ground. Okay? We know that the radius is 0.160. And that the moment of inertia is 0.380. So this is our given information. And we're trying to figure out how fast that 4 kilogram box is going to be moving when it hits the ground. So if we solve this in terms of energy, we can say that basically we can say that the change in potential energy is going to be equal to the change in kinetic energy, because energy cannot be created or destroyed. So we know that if an energy is being lost from kinetic, it must become potential, and vice versa. So we know that this is true. Right. The one thing we forgot to go over actually was the review of the equations. We'll do that right after this problem. Okay, so we know that the change in potential energy is equal to the change in kinetic energy. So let's have a look at what those changes in potential energy are. So every single object, so each of the boxes in this problem are going to have a change in potential energy as they are changing their height. So the change in potential energy of the 4 kilogram box is equal to mgh, which we know is our potential energy equation, which gives us 4 times 9.81 times the 5 meter difference in height, which gives us 196.2 joules if we plug that into a calculator. The 2 kilogram box also had a change in energy, which would be equal to, again, m, mass, times gravity. And what would the change of height be in this part of the problem, Josh?
Well, they're connected by a string, and for the sake of this problem, at least we're assuming this string cannot stretch at all. So if the 4 kilogram box and effectively the string it's connected to move down 5 meters, then we can assume that the 2 kilogram box must do the same and goes up 5 meters.
Exactly. So if there was a positive 5-meter change for the 4 kilogram blocks, we have a negative 5-meter change for the 2 kilogram, which would give us a change of negative 98.1 joules if we plug that into a calculator. So as we know that the pulley wouldn't have potential energy, it would only have kinetic, we can ignore that, meaning that our total change in potential energy, which is equal to our change in kinetic energy, would be 196.2 minus 98.1, which means that the change in potential energy was equal to 98.1 joules. And we can also say that this is equal to the change in kinetic energy. So now, looking at the kinetic energy of the pulley, would we be able to figure out the speed that the 4 kilogram box is hitting the ground at? And we know that velocity is part of kinetic energy, so yes, we can calculate that. So if we take the kinetic energy, well, every object in this problem has kinetic energy. In the case of the pulley, is it rotational or translational?
Well, the pulley isn't actually moving at all besides rotating, so it would just be rotational kinetic energy for the pulley.
Yeah, and what was our equation for that?
Yeah, the moment of inertia I, or 1/2 times the moment of inertia I, and that is times the square of the angular velocity, omega.
Yeah, so that would be our rotational kinetic energy equation. So just plugging in the values we have, which is 1/2 times 0.380. We don't know what omega is, but we know that omega is equal to V over R. This is one of the equations that we've learned before. So that would be that squared, which gives us 1/2 times 0.380 times velocity, which is still unknown, over 0.16. Okay, and if we plug that in, we get kinetic energy of the pulley, the rotational kinetic energy, is equal to 7.4218 times the velocity squared, as this is still an unknown value. And we'll have to leave it like that for the moment. We also have the kinetic energy of the 4 kilogram box. And which equation would we use for each of the boxes, Josh?
Well, that one would just be translational because we're assuming at least that these boxes aren't spinning. So that would just be the typical kinetic energy equation, which is 1/2 times the mass times the translational velocity squared.
Exactly. So we're only using the rotational equation for the pulley. Everything else will have the translational equation. So we have 1/2 times the mass, which is 4 kilograms, times velocity squared, which we also still don't know what the velocity is. But this would give us 2 times velocity squared. Okay. So I will clear this now to give us a little bit more space, but I'll rewrite all of the relevant information. So clear that. So we know that the potential energy is 98.1 joules. The kinetic energy of the pulley was equal to 7.4218 velocity squared. Kinetic energy of the 4 kilogram box was equal to 2 times the velocity squared. And we're solving now the kinetic energy of the 2 kilogram box, which would again be 1/2 mv squared, which gives us 1/2 times 2 times velocity squared, which gives us 1 times velocity squared. Now, as we know that the kinetic energy total is equal to change in potential energy, we can add these together. So we have v squared times 7.4218 plus 2 plus 1. So this is just the sum of all of my kinetic energies from this problem. And that is equal to 10.4218 velocity squared. Now, if I add those all together, I get that the change in kinetic energy is equal to the change in potential energy is equal to this. So I have that 10.4218 velocity squared is equal to my change in potential energy, 98.1. So this will now allow me to solve for the velocity, which is what was an unknown in this problem. So plugging that into a calculator, I get that the velocity is equal to 3.068 meters per second. Okay. Anything to add to that solution, Josh?
I think just kind of a tip for problems along this line. Remember that every single part of the pulley system, I guess, we had to calculate the energy for. It's important not to forget to include the component, because if we hadn't, like, if you think about it, the largest component of the kinetic energy was the rotational, because for the 4 kilogram one, we had 2v squared. The 2 kilogram block, we had just v squared. For the pulley, it was 7.4 v squared. So if we had forgotten to include that, it would have gotten a massively different value. So it's really important to make sure that we always look at every part of the problem. And to be fair, we didn't do anything with the string, but we just assumed it's the, I think we stated it's a massless string, so we don't need to worry about that. So always make sure that you include every component. Think about, you know, how it's changing, where the energy is at in the system. It's really important to make sure we do that.
Yeah, so in this problem, with the exception of the pulley, every single object in this problem had both kinetic and potential. So it's important that you can identify where those energies are present and then be able to calculate those, because only by kind of accurately calculating those values are you going to be able to understand how it's moving, what the velocity is. Okay, so yeah, if there aren't any more questions on that, we will move on to what we were meant to do, which is the equation review. Okay, so I will clear the whiteboard now.
So what we're going to be doing here is we have a list of pretty much every equation that we've used this entire semester. And we figured we'd write them. We kind of have them organized somewhat. And we figured we'd write them down just for repetition's sake. And we'd also talk about, you know, in what kind of problem would that equation be useful. Yeah.
Okay, so we'll start with the kinematic equations. So we know that we have v squared is equal to v initial squared plus 2a delta x. We also have that v is equal to v initial plus a t. And kind of lastly, on the 3 equations that are most used, we have delta x is equal to v initial times t plus 1/2 a t squared. So those would be the kind of 3 most common kinematics problems. And right. Yeah.
So we use these ones mainly in describing motion. The important thing to remember about kinetic equations is we can only use them if we have a constant value for acceleration. Otherwise, they are no longer applicable. Also, just something to keep in mind, you know, I know I talk about this a lot in my sessions. You just got to think like, okay, if I'm not solving for time and I'm not given time, probably don't need to use either of the ones that have time in it. So just, figuring out which variables you do and don't need allows you to narrow it down to which equation ends up being the most helpful for you.
Yeah, it's definitely important to be able to identify your givens and what you're solving for, and then pick the easiest equation out of them. They also have their kind of angular kinematics counterparts to these equations, so they're very similar to the angular kinematics ones. We just replace the variables, so we would have omega squared equals omega initial squared plus 2 times alpha times delta theta, and then omega equals omega initial plus alpha t, and then delta theta equals omega initial t plus 1/2 alpha t squared. So these angular equations are almost exactly identical. We just replace them with their angular variables. Okay. Anything to add to that, Josh?
No, I mean, pretty much the same thing I said about the last one. Just understand that you only need to use the equations that have the variables that you're either given or want to find. So if you aren't, it's the same thing as the last one.
Okay, so these are our kinematics equations. I'll switch to a different color for the next set of equations. So we also have Newton's second law, which is the sum of all forces is equal to ma. And we know that in the case of a problem where the velocity is constant or where there's no acceleration, that will mean that the sum of all forces is equal to 0. And for forces specifically, we know that we have Hooke's law, which is F equals negative K, which is the spring constant, times X, which is the compression or stretch of the spring. Okay, so those are the forces that go along with that. Okay. So we also, as far as acceleration goes, there is the equation for radial acceleration, which is a centripetal equals v squared over r. This can come in handy for circular motion equations. And going back to forces for a second, we also have that the frictional force is equal to the friction coefficient times the normal force. Okay, so those are all kind of forces related to, force and acceleration, basically Newton's second law. Okay. Kind of along the same lines, we have work. So work is equal to force times distance times, I believe it's cosine theta, right, Josh?
Right, yep. And that theta is the angle between the force vector and the distance vector.
Mm-hmm. And then while we're talking about kind of work and energy, basically, we can go over what we just did earlier, which is that kinetic energy is equal to 1/2 mv squared. And then we have potential spring energy, which is 1/2 kx squared, and potential gravitational, which is mgh. So these are kind of equations that we use in that last problem. Yeah, and based on our conservation of energy equation, we know that K1 plus U1 is equal to K2 plus U2. So basically energy is conserved unless it is lost to something like friction. Okay. Let's see. So we also have momentum. We know that momentum is equal to mass times velocity. And we know that momentum is also conserved in the same way as energy for most problems. There are exceptions. Okay. Anything to add to the momentum, work, energy section of those equations, Josh?
I mean, you kind of already said it, but in the conservation of energy equation, that holds true unless there is work done by some other force that is interfering with the kinetic energy and the potential energy. So like friction, for example, isn't dependent on the kinetic energy or the potential energy. So that's the other force until it does work on the system. A lot of times the work done by some other force is usually like the damping force that can stop it, like if it's a pendulum or if it's like friction will stop something from just rolling on further. Yeah.
Okay. So now kind of on the topic of moment of inertia, we have that the moment of inertia is I, and you guys will be given a chart for that. Those will not be equations you need to memorize. But sometimes the moment of inertia isn't what you expect it to be, depending on where it's rotating it around. So we also have the parallel axis theorem, which is that the moment of inertia is equal to the moment of inertia in the center of mass plus the mass times distance from the center of mass squared. So for an object not rotated around its center, this is the equation you'd have to use to convert its moment of inertia to an accurate value.
That's actually how they find that whole table with all the values in different moments of inertia. It's all because of this formula right here. So the most common ones are just given to you. You don't have to use this equation every single time.
Yeah. So this is something that might come up in the problems. Okay. And kind of, going back to energy for a second, we also have that the kinetic energy rotational is equal to 1/2 IW squared. So that's, again, part of energy, but this is for rotational only, not translational. Okay. So we're almost done with our equations here. We have a few more. So we have torque is equal to force cross radius. So we're basically looking at the perpendicular component of the force that is perpendicular to the arm or the lever, the beam, whatever the force is being applied to. And the radius is the distance from wherever you're choosing to call 0 to your force. Okay, so that's torque. And yeah, I will clear this now to give a little bit more space. And then the last thing to go over is just equations for simple harmonic motion. Okay.
Someone has a good question about Hooke's law. So before you clear that,
yeah,
the reason why there's a negative in Hooke's law equation is a distance compressed is a negative x value, which would give you, the negatives to cancel out, would be a positive force. And so if you think about that, if you compress a spring, it's going to have a lot of force pushing in the positive direction. Whereas if you stretch a spring, right, that's a positive x value, you have the force pulling back towards the origin, which would be a negative force value. So the negative sign is just there to demonstrate the direction of the force. So yeah, hopefully that answers your question.
Okay. So I will clear this now. Yeah. So we just have simple harmonic motion left, and for that we have that the frequency is equal to 1 over the period. We also know that omega is equal to 2 pi times the frequency, and that is equal to root k, which is the spring constant, over m in the case of a spring, if this is acting on a spring. Also, for a pendulum, we know that omega is equal to root g over L. So that's for a pendulum. And for a physical pendulum, somewhat similar, we have mgd over L. And this is for a physical pendulum. So this is where the pendulum itself has some shape or mass.
Just a brief correction. I think that for physical pendulum, it's over pi, not over L.
Yeah, for the physical pendulum, it is mgd over I. Okay. Anything else to add to these equations?
I don't think so. I think this is the majority of the equations. I don't know if there might be a couple more, maybe, but I think that's like if you have all of these down, then I don't think you'll find anything that you can't handle on the final.
Okay. So yeah, these are the main equations kind of with the topics that you guys have been learning all semester. So if you know those, it should be possible to solve most of these problems. So yeah, I'll clear this now and we will have a look at problem number 2. Okay, so for problem number 2, we have a physical pendulum. So the rod itself has mass and there is a mass at the end. So a disc of mass 8 kilograms is attached to the end of a 2 kilogram rod, which rotates about the other end as a pendulum. What is the period of this pendulum's motion? So for the case of this example, we're going to treat that disc at the end as a point mass, seeing as we don't necessarily have any values associated with it. We don't have the radius or anything. So we're going to treat that as a point mass. I will move this over to the whiteboard so that we can work on it. Okay. Okay, so for this one, we have a rod and a mass at the end of it. The whole thing is 0.4 meters long. Okay, and 2 kilograms for the rod and 8 kilograms for the disc. So that was all the information we were given. So as this is a physical pendulum, we know from our equations that the equation that we're going to need to use to calculate period is going to involve mgd over I, the square root of that. So we know this is the equation we're going to need to use. In this case, though, in order to use I, we need to calculate that value because we have 2 different objects on here. We know that the center of mass is not necessarily going to be in the middle, as it is, it's got a heavier mass on the bottom. So actually, in order to solve for d, which is the distance from where it's pivoting to the center of mass, we're going to first need to calculate what the center of mass is. So our center of mass equation is that the position of the center of mass is equal to mass 1 times position 1 plus mass 2 times position 2 over the sum of the masses.
What are these positions? Like, because the rod, is pretty long. It doesn't really have one x position. What is what do you mean by x position?
So basically, we're mass 1 times its own center of mass, and mass 2 times its own center of mass. So basically separating this as if it were two separate objects, with one being the rod and one being the point mass at the end. We can then separate them and in that way calculate what their combined center of mass would be. So in this case, mass 1 could be the rod, and its position would be its center of mass, which for the rod by itself would be half that distance. So that would give us 0.2. Whereas in the case of the point mass, its center of mass would be all the way at the end, as we're treating it as if it's just a singular point. So that would be 0.4. So if we were to plug that in, we get 2 kilograms times 0.2 meters plus 8 kilograms times 0.4 meters gives us over a total of 10 kilograms, can be calculated to give a center of mass of 0.36 meters. Okay, so does it make sense how we got that?
Yeah, it also, it's kind of expected. We have the largest mass is concentrated at the bottom of the rod, which means that we expect the actual center of mass to be between the two center of masses, but then closer to the heavier part. So 0.36 is a lot closer to the 0.4 than to 0.2. So that makes sense.
Yeah, and the reason we were able to choose 0.2 as the center of mass for the rod is that in general, a rod will have its center of mass as the center of the rod, a rod by itself with no weights on the end. So we took half that distance. And we're treating this rod as if it's around 0.4 meters long, because we're treating that mass at the end as if it's just a singular point without any real length. So kind of ignoring the length of that disc at the end and treating it as if it's just a point at the end of the rod, we can call the rod 0.4 meters long, and we can say that its center of mass is halfway there. So yeah, the disc is kind of drawn large so that you can see the shape, but in reality, we're treating it as if it doesn't have really any length.
Technically, L is supposed to be the length from the length of the rod, and it's a disc, which is a bit confusing. But think of it like that clicker question that he did in class with that spool where he pulled on it and it moved one direction. The disc is kind of like that. So the rod actually goes through the disc and touches the center. And so 0.4 is technically the length of the rod, and it's also the length from the top of the rod to the center of mass of the disc. It's kind of hard to see, but you can't draw 3D in PowerPoint. So
yeah, so just kind of see the rod as going through the disc. Okay, so the rod itself is 0.4 meters long, which means that the center of mass of the rod, just the rod by itself, would be half the length, which is 0.2. So that's where we get 0.2 from. And we can say that the distance from where it's rotating to the center of mass of the disc is the full length of 0.4 meters, because the rod goes to the center of the disc. So using that, we are able to calculate the center of mass to be 0.36 meters. Okay, so once we have that, that represents the d in the equation above, because that is the distance from the rotating point to the center of mass. Now we just have to calculate what is I. So in this case, we have two objects. So I for the rod is equal to 1/3 times the mass of the rod times the length squared.
And that's something that we can just get from the table. That's not something that has in there.
Yeah, so that's something that we would get from a table. And we know that I for a point mass, which is kind of what we're treating this disk as, would be L squared. So this is kind of a mass that is being rotated at a certain distance, and all of its mass is at one point. So then adding those together to get I total. And we get 8 kilograms plus 2 divided by 3 kilograms times the length squared, which is 0.4 meters. And you plug that into a calculator, and you get 1.387 kilograms times meters squared. So that would be our total value for I, just taken by adding the two I values for each object. Okay, so that would be equal to I in our equation above. So we have I, we have D, we know what mass is, and we know what gravity is, so we can now solve for omega. So I'm just going to clear this to give more space, and I'll rewrite the values. Okay, so D is equal to 0.36 meters. I is equal to 1.387 kilogram times meter squared. And then the mass total is equal to 8 kilograms plus 2 kilograms, which equals 10 kilograms. So plugging that into the equation above, we get 10 times 9.81 times 0.36 over 1.387. And plug that into a calculator, you would get a value of 5.0466 radians per second. But the problem in this case was asking for the period. So kind of going back to our equations, we know that omega is equal to 2 pi f, 2 pi times the frequency, which is equal to 2 pi times 1 over t. So we can say that the period is equal to 2 pi over omega, which gives us 2 pi over 5.0466, giving us a period of 1.25 seconds, and that would be the final answer. Does it make sense how we got to that point?
Yeah, just kind of a lot of calculator work once we figured out the center of mass and the moment of inertia. Once we figured out all of our variables, that's how it is with most of physics. To be honest, is once you figure out all your variables, plug them into the right equation, and you get your answer.
Yeah, so the most amount of work in this problem was just figuring out the variables. We automatically knew which equation to use because it was a physical pendulum. And then once we calculated our values, plugged it in, the math from there was a lot easier. Okay, so if we're all good on this problem, we'll move on to the next one.
Okay. Someone was asking how we calculated I. So we can't exactly go back to that because the whiteboard doesn't save things we've done. But the way we calculated I was the moment of inertia of any system is the moment of inertia of all of the components of that system added together. And so we found the moment of inertia of the rod, which we just pulled from a table, and the moment of inertia of the point mass, or the disk, I guess, and we added those together, and that gave us our total moment of inertia, which was 1.37. And someone else asked if the distance that we use should always be from the top to the end of whatever object we're using. No, the distance is the distance between the center of mass and the axis of rotation. And so at this point, the axis of rotation happened to be at the top. It's something like a pendulum, like hanging from a roof or something. But like, if it was rotating about, you know, the middle of the rod, then the distance would not be 0.26, it would be something else. Yeah, it's less so like thinking of it like it's the top, more so thinking of it, what point is this rotating about?
Okay, so I will clear the board and we'll get started on the next example. Okay. Okay, so for problem number 3, we're looking at momentum. So we have a bullet of mass m is fired at a certain initial velocity and collides inelastically with a block of larger mass m and is lodged into it. This block is hanging on a pendulum of length L, and after the collision, the pendulum swings up an angle of theta. What is the bullet's initial velocity, and what is the resultant period of the pendulum? So we have a given mass of 0.08 kilograms for the bullet, of 3 kilograms for the block, 0.8 meters for the length, and 48 degrees for theta. So I will draw this out on the whiteboard so you can picture it a little better. Yeah. Okay, so for this problem, there is a pendulum with a block on the end of it, and that block is hit with a bullet going a certain velocity, which causes it to swing up at an angle theta. Yeah. The length of the string is 0.8 meters. The block weighs 3 kilograms, and the bullet weighs 0.08 kilograms. Theta is equal to 48 degrees. So the setup of this problem is that the bullet hits the block and forces it to swing upwards. And we are going to use our concepts of energy and momentum in this problem, at least for part A, to solve what the initial velocity of that bullet was. Okay? So at this top point of its swing, what type of energy does it have, Josh?
Well, once it's, I sort of didn't state, we're assuming that that's, you know, its maximum height, which means it would not be moving anymore right at that moment. So the only energy would be potential energy from gravity.
Yeah, so at this point we have potential energy only. And at that point, right where it hits the bullet, what energy do we have? If we're kind of choosing this line here to be 0.
It would just be kinetic energy from the bullet because the block isn't moving.
Yeah, so we have kinetic energy at the bottom. So we don't know from the information we're given what the kinetic energy is at the bottom, but we are capable of calculating the potential energy. So potential energy is equal to mgh, as we know. We know what the mass is. We know what gravity is. But how would we figure out the height?
Well, the height would just be the difference between the natural, sorry, not natural length, but the length of the pendulum um, subtracted by the y component of the pendulum after it's at its max height.
Yeah, so we know that when it swings up to its maximum height, the arm is 0.8 meters long, and it's at an angle of 48 degrees, which will allow us to calculate this kind of value y. And then if we take the full length and subtract from that, we would get the height, which is this value here, which is exactly how high it raised up, which is what we're trying to calculate as far as change in potential energy. So we know that y is equal to 0.8 cosine 48 degrees, which is equal to 0.535 meters. Sorry, let me write that up here. So that's equal to 0.535 meters. And if we want our height, we can subtract our 0.8, that from our 0.8 meters, basically. So 0.8 minus 0.535. That will tell us how high the object was raised, which is equal to 0.265 meters. So our potential energy at that top part of the swing is equal to our total mass, because the bullet is embedded in the wood. So that's 3.08 kilograms times 9.81 meters per second squared times 0.265 meters of height, which gives a potential energy of 7.998 joules. So that will be our potential energy at the top of the swing. And as we've already said, at the bottom of the swing, we only have kinetic energy. And based on our conservation of energy equation, we can say that the kinetic energy at the beginning of the swing is equal to the potential energy at the end of the swing. So we know that kinetic energy is equal to potential energy in this case. So we have 1/2 mv squared is equal to 7.998 joules. And does the velocity in this equation that I've just written down, is that the speed of the bullet initially, Josh?
Well, no, because this is right after the bullet is embedded in the block. So the velocity is the combination of them, which we can probably expect to be substantially smaller.
Yeah, exactly. So this is going to give us the initial swing of the block right after it was hit, but it's not actually how fast the bullet was moving initially. So we still have more steps to go, but this is one step closer. So plugging in our total mass of the combined objects again. We get a velocity of 87.7 meters. Oh, sorry, no, that's the wrong one. We get a velocity of 2.28 meters per second. And that is the velocity of the pendulum at the beginning of the swing. Okay, so from there, which equation or which concept do you think we can use to figure out how fast the bullet was going if we know what the final velocity of the combined was after it was hit?
Well, the equation is, the collision is inelastic, right? Which means that kinetic energy isn't necessarily conserved because some of the energy is lost to the temperature increase of the block, of deforming the block, breaking it, I don't know, without the bullet hitting it. So that means we can't use the conservation of energy. There'd just be too many variables we don't know. However, we can use the conservation of momentum because we know the individual masses and we know one of their velocities, or we know the velocities of the combination of them. So yeah, we just use the conservation of momentum equation.
Yeah. So with the conservation of momentum equation in two different objects, we have the mass and the velocity of the bullet initially, plus the mass and the velocity of the pendulum initially is equal to their combined mass times the velocity of the pendulum afterwards, which is what we just calculated. As we know that the pendulum wasn't moving before it was hit, we can call this value 0. So now it just leaves the mass and the velocity of the bullet initially is equal to the combined mass times the velocity of the pendulum. So that will give us a value of 0.08 times the velocity of the bullet is equal to 3.08 times the 2.28 meters per second that we just calculated. Plugging that into a calculator, you get a velocity of the bullet of 87.7 meters per second. And that will be the final answer. Does it make sense how we got to that point?
Yeah. To be fair, this is probably like an airsoft bullet because it's pretty slow moving for a bullet. It's very fast, but not really compared to an actual bullet speed. But I mean, that's fine. It's definitely substantially faster than that of the pendulum. So that's kind of what we expected.
Yeah, as long as you know how to apply the concepts here, being able to understand conservation of energy, understanding where energy is not conserved, like in the case of a collision here, where the bullet sticks, understanding conservation of momentum and being able to apply those and kind of move through these equations and look at different steps of it, then that's kind of how this equation needs to be solved, just by breaking it into steps. First, you're looking at the swing of the pendulum, then you're looking at the collision of the bullet. Yeah, so that would give you your final answer. If there's no more questions on this, I will move on to part B of this question. Okay, clear the whiteboard. So for part B, we still have the pendulum and its swinging object, but it's asking, in this case, for the period. Now, we know that this is just a regular pendulum. It's got a mass on the end. It's not like the problem in the past where the rod had a certain mass, so we can just use our regular pendulum equation, which is omega equals root g over L. Okay, so using our known values, which are 9.81 meters per second squared and 0.8 meters, which we were given for the length of the pendulum, we get a value of 3.502 radians per second. But again, it wasn't asking for omega, it's asking for period. And from the previous equation that we did, we know that t is equal to 2 pi over omega. So just plugging that in. And we get a period of 1.79 seconds. Okay, does it make sense how we got to that answer?
The interesting thing is that we could have solved for that like immediately without having to do the previous part, because the period of this pendulum does not depend on its velocity. It doesn't depend on its mass. It's solely dependent on the length, and then because gravity is constant. So we could have just solved that one outright. Then you didn't need to. Well, I mean, part A is asking for the other stuff, but part B we could have solved first. Even something interesting to think about.
Yeah. So as it was completely independent of a step, it didn't rely on anything from the previous part of the problem. We can just solve it pretty quickly. It's just about knowing which equation to use. Okay, so there's no more questions on this. We'll move on to the final example. Okay, I'm going to clear the whiteboard then. Okay, so the final problem here is a static equilibrium problem. We've got a bridge with a mass of 18,000 kilograms, and it's 40 meters long, and it's being raised 30 degrees from the vertical while a truck is on the bridge. What is the tension in the wire that is pulling the bridge upwards?
Now, is that 40 meters length, is that referring to just the lifted part, or is that referring to the whole thing?
So that's just referring to the lifted part. So for this example, we're only really going to need to look at that kind of lever part of the bridge, the part that's being lifted. Okay. So I will get the whiteboard out and we'll start working on this problem. Okay, so we have a bridge with a car on it. Treat that as a block for now. There's some kind of hinge here that's allowing it to be lifted. And it is being pulled upwards with some kind of tension, which is what we're trying to calculate. So the bridge is 40 meters. The car is 30,000 kilograms. And the bridge is 18,000 kilograms. Okay, and so that angle between the tension and the bridge is 70 degrees. And 30 degrees from the bridge to the ground, which is what we were given. Okay. There's also a 10-meter distance, a little hard to draw, between the top of the bridge and the center of mass of the truck. Okay, so what we're solving for is the tension in this problem. So seeing as the bridge is being pulled upwards and it's being held there, we know that the sum of the torques must be equal to 0. This problem is in static equilibrium, so we can automatically say that the forces and the torques balance. So we know that the sum of the torques is equal to 0. So let's actually have a look at what some of these torques are on this bridge. We know that there is the torque due to the tension. And remind me, what is our torque equation, Josh?
It's the position vector r from the axis of rotation to the point at which the force is acting. So there's r cross the cross product of the value of that force. So in this case, it would be r cross t.
Right, so we have our force cross radius So in this case, we're basically just looking at the forces that are perpendicular to the bridge. So that will give us our tension force times the sine of 70 degrees would be the perpendicular component times its distance, and that tension is being applied at 40 meters if we're calling the bottom of this bridge 0 to make that as easy as possible. And would this torque be positive or negative, Josh?
Well, we can use the right hand rule. We put our right hand along R and curl our fingers in the direction of T. Our thumb is now pointing towards ourselves, which I believe we define that as positive.
Yeah, and then also if you're kind of just looking at the force and you see that it would be moving that bridge in a counterclockwise motion, counterclockwise would be positive, clockwise would be negative. So say that this is a positive torque. We also have the torque due to the truck. So that's same concept of force times radius. So that would give us the force, which would be the weight, mg. So that's 30,000 times 9.81. But it's, again, the perpendicular component, which would be sine of 60 degrees. And that would be applied at the 30 meters because we know that it's 10 meters down from the top, which means 30 meters up from the bottom is going to give us the center of mass of the truck. So we were given that information. Okay, and that gives 7,000. So we're going to get some quite large numbers here because these are very heavy objects. So 764,613.8 newtons times meters. And would this be negative or positive, Josh?
Using the same kind of logic, we can have the right hand rule or just looking at which direction cause rotation. We could see it would be a clockwise rotation, so it should be negative.
Yeah, so that's negative. And then that just leaves us with one more torque, which is from the weight of the bridge. So torque due to weight, which then gives 18,000 times 9.81 would be our force. Sine of 60 degrees. And this would be applied at the center of mass of the bridge, which would be assumed to be in the middle because it's just the standard beam. So that's 20 meters. And again, this would move it in a clockwise direction, so that would give us a negative torque. And that would give us Newton times meters. So adding those all together, we get that the torque due to the tension minus the torque due to the truck minus the torque due to the weight is equal to 0. So we can now say that the torque due to the tension is equal to the torque due to the weight plus the torque due to the truck. So that's just rearranging those values. Plugging in what we know, we get 40 times t sine of 70 is equal to the sum of our two very large torques. So then just plugging that into a calculator and figuring out the value, you get the tension is about equal to 285,000 newtons. So Newton meters. So it's actually a little higher than that. That's just a rough estimate because it's a very large number. Or it's so it's actually equal to 284,789, but roughly 285,000 Newton meters. And that would be the value of the tension, which is in newtons, actually. So does it make sense how we got to that final answer?
Yeah, it does. That's also a very high tension value. It's impressive for a string or whatever it is. But I suppose it makes sense because we have a 30,000 kilogram car, which is like, or it's a truck, it's like 66,000 pounds almost.
Yeah, so it's got...
It's transporting lots of lead or something. I don't know. It's a very heavy car.
Yeah, it's the bridge has to sustain quite a heavy load, so it's accounting for that, which makes sense that it would have quite a high tension pulling the bridge upwards. And the way we were able to calculate this is just using the concept of static equilibrium and setting our negative and positive values on the right side, adding them up. So yeah, anybody who is able to look at this problem, see negative or positive torques, and understand static equilibrium would be able to get the answer to this question. Once you understand those concepts, the math itself isn't too difficult. Okay. So unless there's any more questions on this, I'll erase this and we can go over any questions on the stuff we've gone over or anything else to do with the class material. Okay, I'll clear the whiteboard.
So at this time, this is your guys' opportunity to ask anything you want. This is our last virtual session, so we'd like to be able to help you guys out as much as we can. So ideally, you guys have questions. They could be about anything, any concepts from the class, any of the problems that we did. I'm going to assume you guys have questions because it's a final exam. You always have questions. So at this point, just feel free to type it into the chat.
So this is our last virtual SI session, but we will be having regular sessions next week, and next week is the last week of sessions.
Well, not next week, just this week.
Sorry, yeah, this week. Today is Monday.
Yeah, I'm not planning on having a session during Dead Day. That does not sound helpful.
No, so next week is the last week of sessions, and that's it.
It's a bit concerning that we're not getting any questions. We want to be able to help you guys. We don't want to, we took some time to get an extended session available. We don't want to have to end 15 minutes early to kind of get you to the whole point.
You guys do have your final coming up, so if there's anything about the final that you've got questions on, I know that it's cumulative for at least a few of the problems. So if there's anything you're wondering about studying, or anything that you kind of went back and looked at and don't understand anymore because you haven't gone over it in a while, we can answer any questions right now.
Right, so someone asked any ideas of what to put on 0 5 cards. I actually forgot you guys get those. Those are in addition to the chapter summary.
I believe that they're not getting the chapter summaries from the earlier chapters, just the ones they've been going over recently. So maybe equations from earlier chapters would be a good idea.
Got it. Yeah, I didn't know that. So maybe that we could even figure out like one of the more difficult concepts from the newer stuff. At least in my last session, it was clear a lot of people needed some practice with statics. Maybe that's the difficult thing with statics, though, is it's very conceptual. Like the formulas are pretty basic. It's just everything equals zero. It's just kind of knowing what to do with it. I mean, as far as tips, it really differs person to person, whatever you think would be beneficial for you. All right. Someone asked, when you took this class, did you find that the professor gave similar questions on the final as the first two in terms of hardest? That is entirely dependent on the professor. Neither Freya or I had Professor Garcia. From what I can tell from his midterms this semester, I don't expect him to be someone who's going to give significantly more difficult problems on the final. It doesn't seem like something he wants necessarily easy. But yeah, I imagine it's going to basically just be pretty similar to the midterm, just with extra problems.
Yeah, I think that his midterms have been pretty reasonable as far as matching kind of what you guys are doing on the homework and in class. The concept, it's kind of nothing new or crazy. I feel like he would keep that pattern up for the final, but again, neither one of us knows what the final is going to be like.
Any other questions regarding concept? It's not card double-sided. That is a good question. I imagine so.
I believe so. I think he said that it was, but that might be something to double check. Yeah.
Someone said yeah. So, I mean, I imagine, yeah. Like, if professor's going to only give you a 3x5 card, I'm pretty sure they'd probably give you both sides. Otherwise, it's like 4 equations. But yeah. All right. Well, if there's no more questions, make sure you ask them now. Otherwise, we're going to call it. All right. Yeah, the recording will be posted as soon as possible. You still have to edit the video, send it, and render it and upload it. So I can't guarantee it'll be today, but hopefully as soon as possible.
Yeah, and as far as our sessions go, I have a session 12 to 1 on Wednesday. Josh has one 3 to 4. Yeah. And then Thursday I have office hours 3 to 4. And Friday Josh has a session, I think, is it 12 to 1 or 1 to 2?
1 to 2.
1 to 2, yeah.
There's technically 4 more sessions that you guys can attend. So really, even if you unfortunately waited to the last week, it just means, you have to attend 3 in 1 week. Although I suppose only 2 now if you've attended this one. So this one counts towards it as well. All right. Well, thanks for attending. We will see you guys in class tomorrow. Anyway, to record the in person. Oh no, definitely not. Sorry, but it would take like a whole video camera, and it would not work out.
Yeah, the virtual sessions are meant to be an additional resource, but the SI sessions in general are meant to be an in-person thing so that we can work more individually with students.
Yeah. It's also a very different kind of environment. Like, obviously, if it was just me, like, this would be a really boring session. Because I'd just be me talking to myself. But because there's me and Freya doing the session, it's able to still be more conversational. Whereas, you know, in our in-person sessions, it's just one of us, so that wouldn't work out very well. But all right, guys. We will see you guys tomorrow in class. It's been a good time doing virtual this year. This is actually both mine and Freya's first time doing this, and it's actually a brand new program. We only had, I think there was like one class last semester that had virtual SI. So it's kind of, we're still working on rolling it out. So hopefully it's been helpful, and good luck with your studying.
Yeah, good luck with your last week of classes, guys, and we'll see you in class. Okay, I'm going to stop the meeting now.